Hi, guys, and welcome to the AP Chemistry November comeback. Today we're going to cover Unit 1. So I hope you printed out Unit 1 from our Canvas course, and I'm going to share my screen. There we go. So we are reviewing Unit 1 of AP Chemistry, and the first topic we're going to go over is atomic structure, isotopes, and ions. Remember, the atom is made up of protons and neutrons in the nucleus. Protons are positively charged, neutrons are neutral, and the electrons are negatively charged, which exist in shells or energy levels outside of the nucleus. The atomic number Z is the number of protons in an atom and is also equal to the number of electrons in a neutral atom. The mass number, remember, is the number of protons plus the number of neutrons, and it is not included in the periodic table. Rather, the periodic table is the average atomic mass. Let me clean this up. The periodic table is the mass on the periodic table is the average atomic mass, a weighted average of all the naturally occurring isotopes of an element. So let me go back here. Remember, the periodic table is arranged by atomic number. That is the number of protons in the nucleus of an atom, and it's in a neutral atom, and atoms are neutral. Number of protons are equal to the number of electrons. Isotopes are atoms of the same element. They have the same number of protons, but they have a different number of neutrons. So they have different mass numbers. Ions, on the other hand, are different from isotopes. Ions have the same number of protons, or let me say it another way. An ion is an atom with a charge. So if an atom loses electrons, it's going to be an ion because it has more protons than electrons, so it's going to be positively charged. Whereas if an atom gains electrons, it now has more electrons than protons, so it's going to be negatively charged. So let me do this sample problem for you. Write the nuclide symbol for an atom that has 19 protons, 20 neutrons, and 18 electrons. Remember, in a nuclide symbol, you're going to put the actual number, excuse me, the shorthand notation, the symbol for the atom. And so if we have 19 protons, we're looking for an element with 19 protons, that's potassium. So we know it's potassium, and the bottom left-hand corner is always the atomic number, which is the number of protons here, 19. And the mass number is on the upper left-hand corner, and that's the number of protons plus the number of neutrons. So that number is going to be 39. And because it's got one fewer electron than protons, it actually has a plus charge because it's short one electron. What I want you guys to do is do practice 1A, fill in the table, and then we'll do it together. I'll give you a couple minutes. In our first row, they're telling us it's chloride, an atomic number, Z, of 17, and a mass number of 35. That means there are 18 neutrons. That's already filled in here because 17 plus 18 is 35. The number of electrons, notice it's a negative charge, so that's one more electron than protons. The charge, of course, is -1, which makes it an ion. Remember, an ion is an atom with a charge. Here we have iron 2 plus. We know that there are 26 protons. They told us right here. The number of neutrons is going to be 58 minus 26, which is, I believe, 33. Right? 58 minus 26. 32. I take that back. Let me do that, 32. It has 2 electrons less than the number of protons because it's 2 plus. So 2 electrons less than 26 is going to be 24 electrons. Its charge is +2 and it's an ion. Here's an equation. The charge is equal to the number of protons minus the number of electrons. Okay? So if my charge is +2 and I know it's 26 protons, the number of electrons is going to be 26 minus 2, which is 24. And the final one has 55 protons. So let's look on our periodic table for 55. That's cesium. 55 protons, 77 neutrons. So to put the mass number, 77 plus 55 gives me 132 as a mass number. The charge is +1. So remember, I'll do it 2 ways. The charge is +1, which tells me, let's put our +1. It tells me it's an ion, and it tells me I have one fewer electron than proton, so it's 54. But if I use this equation here, charge +1 is equal to protons minus electrons, we would know that electrons is equal to 54. So let's do the multiple choice question here. Which pair are isotopes of the same element? I'll give you about a minute to answer this question. If that didn't need a minute, if you answered letter B, you're correct. Remember, isotopes are the same atoms with different mass numbers. Let's move on to page 2, the mole and molar mass. We have two major conversions here. We have 1 mole is equal to 6.02 or 6.022 times 10 to the 23rd particles, and the mass in grams is equal to the moles times the molar mass. Okay, so we know that mass, or the molar mass, grams per mole of an atom, is the mass of 1 mole, and we get that from the periodic table. So here we have a sample problem. How many atoms of oxygen are in 10 grams of CO2? So we can't go directly to atoms of oxygen. We have to go, since we have CO2, we have to go to molecules of CO2. So, but I'm going to start. How many atoms of O, are in 10 grams of CO2? When I'm given grams, I need to cancel out grams. That tells me I need the molar mass of CO2. Carbon has a mass of 12.01 plus 2 oxygens makes a molar mass of 44.01. So the grams cancel out. Now I have moles of carbon dioxide. I need to go from moles of carbon dioxide. I can't go straight to atoms of oxygen, but I can go from moles of carbon dioxide to molecules of carbon dioxide. 1 mole of CO2 is equal to 6.022 or 6.02 times 10 to the 23rd molecules. Okay, so the moles of CO2 will cancel out, and I'll be left with molecules. Once I have molecules, then I can convert molecules to atoms because I know, let me do another conversion factor here. I know that 1 molecule of CO2 contains how many atoms of oxygen? Right, 2 atoms of oxygen. So that's our whole dimensional analysis process. We're going to multiply all the numerators together and divide by all the denominators. So it's 10 times 6.022 times 10 to the 23rd times 2, it's 2 atoms per molecule, divided by 44.01 gives me, we can put the answer here, it's right here actually, Well, actually, my rounding here is a little bit different. It's 2.74 times 10 to the 23rd atoms of oxygen. Any questions about that? So in practice 2A, I want you to convert 5 grams of aluminum to atoms. Okay. Since aluminum is an atom, we don't have to go to molecules and then atoms. We can go straight to atoms from moles. So solve that problem. I'll give you a couple minutes and then we'll solve it together. Okay, so how many aluminum atoms, question mark Al atoms, are equal to 5 grams? Since we're starting with grams, 5 grams of aluminum that is, I need to divide by grams, which is going to be the molar mass of aluminum. So 1 mole of aluminum has a mass of 26.98 grams per mole. Once I've converted that to moles, then I can convert that straight to atoms because I know that 1 mole, again, I'm going to cancel out moles. 1 mole of aluminum contains 6.022 times 10 to the 23rd atoms. So 5 times 6.022 times 10 to the 23rd. Again, I'm multiplying the numerators and dividing by the denominator, and I get, let me find a place to put my answer. I get, there is no place to put my answer, 1.12 times 10 to the 23rd atoms. And next, try practice 2B. How many grams of sulfur dioxide contain 1.806 times 10 to the 24 molecules? How many grams of SO2 contain 1.806 times 10 to the 24 molecules? So you're going to start. How many grams of SO2 are equal to 1.806 times 10 to the 24 molecules? Hey guys, I feel like I'm running out of room, so I'm just going to put this on a new page. How many grams of SO2 are equal to 1.806 times 10 to the 24 molecules? Since I'm given molecules, I need to divide by molecules. And I know that there are 6.022 times 10 to the 23rd molecules in 1 mole of SO2. Once I convert molecules to moles of SO2, then I convert moles of SO2 to grams, and that's the molar mass, right? So sulfur is 32.06 plus 2 oxygens, which are 16 each. So its molar mass is 64.06. The moles will cancel out. Again, I'm going to multiply by the numerators. 1.806 times 10 to the 24 times 64.06 divided by 6.022 times 10 to the 23rd. And I get, looks like 4 sig figs here, right? So it's 192.1 grams of SO2. Okay, practice 2C is multiple choice. A sample of sulfuric acid contains 9.80 times 10 to the 24 molecules of sulfuric acid. What is its mass in grams? So again, we're going from molecules to grams, just like in the previous problem. Type in the letter corresponding to the best answer. Okay, so how how many grams is 9.80 times 10 to the 24 molecules of sulfuric acid? We know that there are 6.022 molecules per mole. And we know that the mass of sulfuric acid H2SO4. So we have two hydrogens, 2 times 1.008, plus sulfur, which is 32.06, plus 4 oxygens, 4 times 16, is 98.076 grams. So we put 9.8, let me do that again, 9.8 times 10 to the 24 times 98.06 divided by 6.022. Oops, I left out times 10 to the 23rd. That's important. And I get 1596, or on 3 sig figs, it would be about 1600. No, that would be 2 sig figs. So 1.60 times 10 to the third. There we go. Letter C. And finally, in this section, practice 3C, another multiple choice question. Two students each have 1 mole of a substance. Student A has sulfuric acid and student B has calcium nitrate. Which student has the greater number of atoms and by what factor? I'll give you about a minute to ponder this one and then we'll go over it. So they each have 1 mole, so they each are 6.02 times 10 to the 23rd molecules. But how many atoms do they have? So H2SO4 is 2 hydrogens plus 1 sulfur, that makes 3, plus 4 oxygens. So H2SO4 has 7 atoms, and calcium nitrate has, well, nitrate, NO3, is 4 atoms times 2 is 8, plus calcium is 9 atoms. So since they each have a mole of molecules, calcium nitrate has more atoms in a mole. So I would say calcium nitrate is B by a factor of 9 divided by 7, about 1.3. Okay, let's move on to section 3, mass spectroscopy and average atomic mass. Remember, when you have a mass spectrograph, each peak is the mass of a certain isotope, and the height indicates the relative abundance of that isotope. And remember, the average atomic mass is the sum, that's the sigma, of the fractional mass times the mass of each isotope. So here we have the mass spectrograph of chlorine, and it's got one atom at an intensity of 100 and another atom. They don't really give us this. It's not 24.24 because I guess that would be 75.76. So I would use these because these must be the fractional percentages. So I would take again, the fractional percentage, 0.7576 times 35, plus, that's a 7, by the way, plus the fraction of isotope 37.2424 times 37, and that's going to give me the average atomic mass, 0.7576 times 35 plus 0.2424 times 37, and we get an average atomic mass. It's hard to talk sig figs here, but these are to the hundredths place. So let's do it to the hundredths place. 35.48 grams per mole, or we could say AMU. How about that? AMU. Data interpretation. Number 1, if the 35 chlorine peak is 100 units tall, predict the height of the 37 chlorine peak, chlorine 37. And then I'll let you do that one, and then we'll go on to number 2. I'll give you about a minute to figure that one out. Okay, so we'll solve this with a simple ratio. We want to we know that the 35 peak is 100. So we say 100 is to 75.76 as X is to 24.24. So in other words, 100 divided by 75.76 times 24.24 is going to give me a height of about 32 units tall. Number 2, determine the average mass of the element in this spectrograph. Okay, so I want you to figure out the average atomic mass of this spectrograph. I'll give you about a minute or 2. So we want to make sure that each one of these peaks adds up to 100%. So let me just add these percentages. 4.3 plus 85.1 plus 8.2 plus 2.4. Yes, that is 100%. So I can just take 4.3, or the fractional amount, times 50. So 0.043 divided by 100. 0.043 times 50 plus 0.851 times 52 plus 0.082 times 53 plus 0.024 times 54. So 0.043 times 50 plus 0.851 times 52 plus 0.082 times 53 plus 0.024 times 54 gives me an average atomic mass of 52, about 52.0. Everything here is to the 10th place, so I'm going to give my answer the 10th place. So that is equal to 52.0. And how do I check that I'm right? Well, it's definitely around these numbers, right? And it's pretty much at 52, which is the tallest peak, so that would make sense. Now answer the multiple choice question, practice 3B. In a mass spectrometer, heavier isotopes are deflected more than lighter, less than lighter, equally, or randomly. Yeah, you guys got that. Got that pretty quickly. In a mass spectrometer, heavier isotopes are deflected less than lighter. Heavier particles move less than lighter particles. Lighter particles are easier to deflect. Let's move on. Percent composition and empirical and molecular formulas. So here's the little poem. This is how to solve empirical formulas. Percent to mass, mass to mole, divide by small, times to whole. And that's all you have to do to solve these problems. So we have a compound that's 50% S. So we're just going to assume we have 100 grams. So we have 50 grams of sulfur and 50 grams of oxygen. Then we're going to convert grams to moles by dividing by the molar mass. So 50 divided by 32.06 is 1.5596. I'm just rounding wherever it feels good. Where it feels right, because this is a ratio. 50 divided by 16 is 3.125. That's percent of mass, mass to mole, and I divide by small. I divide each of these by the smallest of these two numbers, which is 1.5596. 1.5596. This is equal to 1. 3.125 divided by 1.5596. Oops. Let's try it again. 3.125 divided by 1.5596 gives me 2. So the empirical formula is 1 sulfur and 2 oxygens. Before you do an empirical formula problem, do the percent by mass of each element in nitric acid, HNO3. Okay, so to figure out the percent composition, we need the masses of each of these elements. So hydrogen is 1.008. Nitrogen is 14.01. Again, I'm getting these from the periodic table. And 3 oxygens is 3 times 16. So the total molar mass of nitric acid, 1.008 plus 14.01 plus 3 times 16 is 63.018 grams per mole. The percent hydrogen is the mass of hydrogen over this number times 100. Which is, let's say 1.60%. The percent of nitrogen is going to be 14.01 over the total molar mass. Is 22.23%. And the percent oxygen is 3 times 16 over the molar mass. Which is 76.17. And you can eyeball to see if you're right. Do these add up to 100%? 76 and 22 is 98, 98.4, and with hydrogen is 99.4 plus 0.6 is going to be 100%. I don't know if you recall doing combustion analysis, but remember, when you have combustion analysis, you've got a hydrocarbon plus oxygen makes carbon dioxide and water, right? So if we have 1.10 grams of carbon dioxide and 0.450 grams of water, we know that all the carbon comes out as carbon dioxide and all the hydrogen comes out as water. So we figure out how much carbon is in carbon dioxide, how much carbon is the 1.10 grams of carbon dioxide, and how much hydrogen is in 0.450 grams of water. We can then figure out the grams of carbon and hydrogen in the original compound and then put it through our little empirical formula poem, percent to mass, mass to mole, divided by small times to whole. I'll give you some time to work on that. Okay, so to find how much of the 1.10 grams of carbon dioxide is carbon, we're going to multiply that number by the mass of carbon over the total mass of carbon dioxide. So in other words, the fractional amount of carbon dioxide that is carbon. So carbon dioxide has a molar mass of 44.01 and carbon is 12.01. 12.01 divided by 14.01 tells me that the carbon dioxide is 27.3% carbon. I'm going to multiply that by 1.10, and that tells me that I have 0.300 grams carbon. Let me do the same thing with water. With water, I'm going to multipy that by 2 because it's got 2 hydrogens. So I need to figure out what mass of what percent or what fraction of the mass of 0.450 grams is hydrogen, and that all comes from my original hydrocarbon. So it's 2 times 1.008 grams per mole over the entire molar mass of water, which is 18.016. So 2 times 1.008 divided by 18.016 gives me, oh, and then I'm going to multiply that by 0.450, and I get 0.0503. I'm just going to keep these numbers here and keep them long so to make the ratios easier. So 0.050355 hydrogen. To figure out the empirical formula now that I have grams, so I don't have to do percent to mass because I already have mass. But the poem is percent to mass, mass to moles, divided by small times to whole. So we need to convert these to moles. So 0.300 grams divided by the molar mass of carbon and 0.05 grams divided by the molar mass of hydrogen. So 0.300 divided by 12.01 gives me 0.025, and 0.050355 divided by the molar mass of hydrogen gives me 0.05, really, right? I'm going to divide each of these by the smallest. The smallest is 0.025. 0.025. This is 1. I'm assuming this is 2. Sometimes I make mistakes, so I'm just going to do that. Yeah, it is 2. So the empirical formula of this hydrocarbon is CH2. Practice 4C. Determine a compound's molecular formula given its empirical formula and its molar mass. See if you remember how to do the molecular formula. I'm just going to give you a minute to do this one. So to figure out the molecular formula, the molecular formula is going to be a whole number ratio of the empirical formula. It could be equal to let me say that again. The molar mass of the molecular formula is going to be a whole number ratio of the empirical formula. So to figure out the molecular formula, I'm going to take the molar mass of the molecular formula and divide it by the molar mass of the empirical formula. The molar mass of the molecular formula, they're telling us, is 56 grams per mole. The molar mass of the empirical formula contains 1 carbon, which is 12.01, and 2 hydrogens, 2 times 1.008. So it's 14.026. So 56 divided by this number should give me a whole number. And that whole number is 4. So the molecular formula then is 4 times CH2 or C4H8. Finally, practice 4D. A compound is 65.5% carbon, 5.5% hydrogen, and 29% oxygen. Determine its empirical formula. Percent to mass, mass to mole, divide by small, times to whole. You can pause the video here to solve this. Otherwise, I'm just going to go straight through. So we've got 65. I'm actually a little worried about space. Let me just do this on a separate piece of paper. Separate page, really. That'll work good. Okay, so let's go back here. We're going to go percent to mass. So 65.5% is 65.5 grams of carbon, 5.5 grams of hydrogen, and 29.0 grams of oxygen. Percent to mass, mass to mole. So we divide by the molar mass. 65.5 divided by 12.01 is 5.454. 5.5 divided by 1.008 is 5.456, pretty much the same number. And 29 divided by 16 is 1.8125. So percent to mass, mass to mole, that's where we are now, divide by small. So I'm going to divide them all by the smallest, which is 1.8125. .454 divided by 1.8125 gives me 3. This is going to give me 3 as well, and this is going to give me 1. So the empirical formula is C3H3O, which is not one of these. Interesting. C3H3O. I think I'm right. Okay. Well, we're going to do C3H3O. Okay, moving on. Page 5, composition of mixtures. Mixtures are physical combinations of substances, and their composition can vary. We look at it in 2 different ways in AP Chem, at the particle level and quantitatively via mass or percent by mass. Here's a particle representation. What is the percent of this component in this mixture? For one thing, you can tell it's a mixture because it's got 2 different types of molecules. It's got the striped molecule and the Mickey Mouse looking molecule, which is usually what we use to represent water. So the percent of our striped molecule is 2 of them over 5 total. So that is going to be 40%. Quantitative mixture problem. A 2.40 gram mixture of calcium chloride and sodium chloride together contains 0.12 grams of sodium. Okay, so what percent of the sample is sodium chloride? What we need to figure out is how many grams of this mixture is sodium chloride over the 2.40 times 100. That will give us percent. We can figure out the number of moles of sodium, and we know in NaCl, it's a 1-to-1 ratio, right? So how many moles is 0.12 grams sodium? We are going to divide by its molar mass, 22.99 grams per mole. Gives us about 0.0052 moles of sodium. Okay, and that means we have, because it's 1-to-1, we have 0.0052 moles of chlorine as well. So how many grams is that? How many grams? Or I can just do, let me do it this way. How many grams of sodium chloride is 0.0052 moles of sodium chloride? 1-to-1 ratio, right? I'm going to multiply it by the molar mass. So sodium is 22.99 and chloride is 35.45. So it's 58.44 grams per mole. 0.0052 times 58.44 gives me 0.31 into sig figs, 0.31 grams of, what did I do wrong here? 0.0052 moles. Let me just make sure I did that right. 0.12 divided by 22.99 gives me 0.0052 moles. 0.0052 moles. Oh, it's divide. I saw 0.12. I'm sorry, over 2.40. Let me just check my numbers again. 0.0052 moles times 58.44 gives me 0.31 or 0.30. Did I do it differently each time? Yeah, 0.305 grams. I divide that by my original mass, which is 2.40 times 100. I'm going to take this number originally, divided by 2.4 times 100, and I get about 12.7% of that mixture is sodium chloride. Do practice problem 5A. Let's do this problem together. In the interest of time, what percent of this mixture is calcium carbonate? Okay, so if we know we have 1.50 grams of carbon, how many moles of carbon is that? So how many moles of, why did I say carbon? How many, let's rephrase. We know we have 1.50 grams of calcium. How many moles of calcium is that? The molar mass of calcium is 40.08 grams per mole. So 1.50 divided by 40.08 gives me 0.0374 moles. So what is the mass, how many grams of calcium carbonate, which is a 1-to-1 ratio between calcium and carbonate, is equal to that number of moles. So I'm going to multiply that by the molar mass of calcium carbonate. Calcium we know is 40.08. Carbon is 12.01. And 3 oxygens is 3 times 16. It's 100.09. So 0.0374 times 100.09 gives me 3.75 grams of calcium carbonate. Over my entire mixture times 100 divided by 5 times 100 is going to give me 74.36 figs, 74.9%. Practice 5B, multiple choice. In a mixture analysis, assuming complete reaction of one component implies complete reaction means that all of the limiting reactant is consumed. Okay, moving on to section 6, Coulomb's law and periodic trends. The core idea is that the attraction of electrons for the nucleus is a function, this is the equation for Coulombic force, is proportional to the charge of the nucleus divided by the distance squared. When the effective nuclear charge increases and the distance decreases, the Coulombic force increases. It's a stronger attraction. When Coulombic force increases, so does ionization energy, so does electronegativity, and when Coulombic force increases, radius decreases. Sample problem 6. Rank lithium, carbon, oxygen, and fluorine by first ionization energy. It doesn't say the order, so let's go lowest to highest. Lithium, carbon, oxygen, fluorine. From lowest to highest, Zeph increases this way. So of all of these, fluorine is going to be the largest. So I would say lithium, then carbon, then oxygen, then fluorine. Practice 6A. Which pair best illustrates the trend in atomic radius down a group? As we go down a group, radius increases because we're adding additional energy levels. We're adding additional energy levels. The valence electrons are further from the nucleus, decreasing the Coulombic attraction. So is lithium larger than sodium? No, lithium is above sodium, so lithium is smaller than sodium. Is sodium smaller than potassium? Yes, sodium is smaller than potassium, as sodium is above potassium. Let's look at the other ones to make sure. Is calcium larger than cesium? No, cesium's down here. Cesium is larger. Did I say calcium again? Potassium. I hope I didn't mess that up. Potassium is smaller than cesium. And is beryllium larger than magnesium? No, beryllium is smaller than magnesium. So our first answer that we came up with, I think it was letter B, is correct. Part C. Using Coulomb's law, justify why aluminum has a lower first ionization energy than magnesium. We would expect actually aluminum to have a higher ionization energy than magnesium. So let's see what's going on. Why would it be lower? Well, we already talked about how aluminum has this extra peak, right? So what they're saying is it actually takes less energy, even though aluminum has a higher effective nuclear charge, it takes less energy to remove the 3p electron than the 3s2 electron. Why would that be? If I were to use Coulomb's law, again, I'm going to take it at face value that AP Chem is not going to tell me something wrong. So I have to figure out why. So I'm going to say, what did they say that just using Coulomb's law? Okay, so I'm going to say that the 3p electron is further from the nucleus than the 3s electron. So because it's at a greater distance from the nucleus, even though aluminum has a slightly larger effective nuclear charge, because it's further from the nucleus than the 3s electron, and because the 3s orbital may be doing some shielding between the 3p orbital and the nucleus, it's going to take less energy to remove the one 3p electron from aluminum than it is the 3s2 electron from magnesium. Mini FRQ number 2, mass spectroscopy and isotopic analysis. The mass spectrum of a naturally occurring element X shows two peaks at 62.93 and 64.93 with relative intensities of 69.1 and 30.9 respectively. Calculate the average atomic mass. Okay, so since we have these two intensities, we're going to have to figure out the fraction of each. So if we have 62.93, we're going to have to multiply that. We don't have percentages here or fractional, but we know that 62.93 is 69.1 over the sum of 69.1 plus 30.9. So that's the total intensity. And we know that 64.93, we multiply that by 30.9 over the total intensity, which is 69.1 plus 30.9. So let's see if we can put this in our calculator. 62.93 times, and I put in parentheses, 69.1 divided by 69.1 plus 30.9, close parentheses, plus 64.93 times, open parentheses, 30.9 divided by, open parentheses, 69.1 plus 30.9, close parentheses, gives me an average atomic mass. This is into the hundredths place, so I'm going to put my answer in the hundredths place, 63.94 AMU. Identify the element X, 63.94 AMU. 63.94. I'm going to assume that that is copper. It's the only thing that's close. That's the closest number to that. 63.55 is the closest, 63.94 copper. A second sample of element X was synthesized and found to contain 90% of the lighter isotope. Calculate the new average atomic mass and explain qualitatively how its spectrum would differ from the natural one. So if 90% of it is the lighter one, which is 62.93, that means that only 10% would be the other one, which is 64.93. So 0.9 times 62.93 plus 0.1 times 64.93 gives me 63.13 AMU. We'd expect the AMU, qualitatively how it would differ. Oh, the spectrum would differ. Okay. Well, we'd expect the AMU to be closer to the 62.93 because it's a larger abundance than the other one. The other abundance, if I actually calculate that, is 69.1 divided by the sum of 69.1 plus 30.9. The other one is only 69%. This is 90%. That's why it's closer to 63. How the mass spectrum would differ, it would be a much larger peak at 63, right? It would be, if this were 100, right? And that's a 5, 6, 7, 8, 9. The 63 peak would go all the way up to like 90. Is that 60? That's a 63 peak. Sorry, I put down the wrong number. The 63 peak would be all the way up to 90 or 62.93. And the 65 peak or 64.93 would only be at 10, which is probably about like that. Explain why the peaks appear integer values of m over z, even though the weighted average is not an integer. Okay, let's change these to integer values. The reason why these are whole numbers, these are the mass numbers. It's a counting number, the number of protons plus neutrons in an atom. Whereas the weighted average is not an integer because it is a weighted average. It's not a counting number. So a weighted average, like a GPA, like if you have all A's, you have a 4.0. But if you add in a B, you're going to add up and having more decimal places to your number. Just because that's a weighted average and not a counting number, we're going to get a decimal, not an integer. Okay, we're done. I hope you enjoyed this session of our new November comeback, reviewing Unit 1. And I'll see you on Friday for the November comeback Unit 2 review. Take care.